Stealth aircraft are often described as invisible machines, able to pass through defended airspace without ever being seen. They are frequently portrayed as mysterious, defined by unusual shapes and advanced materials. But those descriptions do not fully explain how stealth works, what problem it was designed to solve, or why aircraft like the B-2 Spirit, F-22 Raptor, or F-117 Nighthawk are built so differently. It's not actually invisible, but radar can't see it. Here's how that's possible. When people hear the word stealth, they tend to imagine something close to science fiction, a jet that vanishes into thin air, a machine that can't be seen, tracked, or touched. But stealth is not invisibility, and it was never meant to be. It's a carefully engineered solution to a very specific problem: how to control detection in a world where radar dominates the battlefield. Modern air combat does not rely on eyesight. It relies on sensors, and the most important of those sensors is radar. Radar works by sending out radio waves and waiting for them to return. When those waves hit an object, some of the energy reflects back toward the radar system. That returning signal tells the operator that something is there, how far away it is, and sometimes how fast it's moving. The stronger the reflection, the clearer and more reliable the detection. Traditional aircraft were never designed with this in mind. Their shapes were optimized for aerodynamics, speed, and lift. Rounded fuselages, vertical tails, exposed engine components, these all interact with radar in ways that produce strong reflection. When radar waves hit these surfaces, they bounce back in many directions, and a significant portion returns directly to the source. On a radar screen, that creates a bright, obvious signal. Stealth aircraft take a completely different approach. Instead of maximizing aerodynamic simplicity alone, they're designed to manage how radar waves behave when they strike the aircraft. The goal is not to eliminate reflection entirely, but to control it in a way that minimizes what returns to the radar receiver. This is where shape becomes the foundation of stealth. One of the earliest and most striking examples of this idea is the F-117 Nighthawk. At first glance, it looks unnatural. Instead of smooth curves, it's made of flat, angular surfaces. That design is not about airflow in the traditional sense. It's about directing radar waves. Each surface on the aircraft is angled in such a way that when radar waves hit it, they're reflected away from the source rather than back toward it. Imagine shining a flashlight at a mirror compared to a tilted piece of glass. If the angle is right, the light will reflect off in a completely different direction instead of returning to your eyes. The F-117 applies this concept across its entire structure, using carefully calculated angles to scatter radar energy. What makes this approach effective is not randomness, but precision. The angles are not arbitrary. They're aligned so that radar waves are consistently redirected away from the threat. This reduces the amount of energy that returns to the radar system, making the aircraft appear much smaller, or sometimes causing it to blend into background noise. The F-117's design also reveals the limitations of early stealth technology. Its faceted shape exists partly because of the computational limits of its time. Engineers could only model radar reflections using flat surfaces, so they built the aircraft accordingly. It's a solution that works, but it's not elegant. As technology advanced, designers found ways to achieve the same radar deflecting effect using smoother, more continuous shapes. This is where aircraft like the B-2 Spirit came in. The B-2 does not rely on obvious flat panels. Instead, it uses a flying wing design, with smooth curves that guide radar waves away from the source. The entire aircraft is essentially one continuous surface, with no vertical tail and minimal protrusions. This eliminates many of the features that typically create strong radar reflections. The principle, however, remains the same. Whether through sharp angles or smooth curves, the goal is to prevent radar waves from bouncing straight back. Shape controls direction. It determines where the energy goes, and more importantly, where it does not go. But even with perfect shaping, some radar energy will still reflect back. No surface can redirect everything. This is where materials come into play. Stealth aircraft are coated in specialized substances known as radar-absorbent materials. These materials are designed to do something very specific: absorb incoming radar energy and convert it into a tiny amount of heat instead of reflecting it. In simple terms, if shaping reduces most of the reflection, these materials reduce what is left. They act as a secondary layer of defense against detection. When radar waves hit the aircraft, a portion is already being deflected away. The remaining energy is then absorbed, further weakening the return signal. This combination of shape and material is what defines stealth. One without the other would not be nearly as effective. Shape handles the bulk of the work by controlling direction, while materials reduce residual reflection. However, stealth design goes far beyond just the outer surface. Every detail of the aircraft must be considered, because even small features can create strong radar returns. Take engine inlets, for example. Inside a jet engine are spinning compressor blades made of metal. These blades are highly reflective to radar. If radar waves can reach them directly, they can produce a very strong return signal, strong enough to compromise the aircraft's stealth. To solve this, stealth aircraft hide their engines deep within the fuselage. The air intakes are designed with curves or S-shaped ducts that block a direct line of sight to the engine face. Radar waves entering the intake are either absorbed or redirected before they can reach the reflective components. Weapons present another challenge. Traditional aircraft carry missiles and bombs on external pylons. These create additional surfaces that reflect radar, increasing the aircraft's visibility. Stealth aircraft avoid this by carrying their weapons internally. Inside the aircraft are weapon bays that remain closed during flight. When it's time to engage a target, the doors open briefly, the weapon is released, and then the doors close again. This minimizes the time during which the aircraft's radar signature is increased. Even the smallest design elements are carefully controlled. Panel edges, seams, and joints are aligned in specific directions to avoid creating unintended reflections. The edges of wings and control surfaces are often set at matching angles so that any reflected radar energy is directed consistently away from the source. Another factor that must be managed is heat. Radar is not the only way to detect an aircraft. Infrared sensors can detect the heat emitted by engines and exhaust systems. While this is a different part of the electromagnetic spectrum, it still represents a vulnerability. Stealth aircraft attempt to reduce their infrared signature through several methods. Engines are often buried within the aircraft structure, shielding them from direct view. Exhaust gases may be mixed with cooler air to reduce their temperature, and the exhaust itself may be spread over a wider area to make it less concentrated. The B-2 Spirit is a clear example of this approach. Its engines are embedded within the wing, and its exhaust is designed to minimize heat visibility. This does not make it invisible to infrared sensors, but it reduces the distance at which it can be detected. All of these elements work together to achieve a single outcome: a reduced radar cross-section. Radar cross-section is a measure of how detectable an object is to radar. It doesn't directly correspond to the physical size of the object. A large aircraft with effective stealth design can appear on radar as something much smaller. In some cases, it may resemble a bird or a small piece of debris rather than a combat aircraft. This is where the real advantage of stealth becomes clear. It's not about being completely invisible, it's about changing how you appear to the enemy. A stealth aircraft might still be detected under certain circumstances, but the detection may be delayed, uncertain, or ambiguous. Radar operators might see a weak or inconsistent signal that does not immediately register as a threat. By the time the aircraft is recognized for what it is, it may already be too late. This delay is critical. In combat, time is of the essence. The earlier you detect an opponent, the more options you have. You can track, intercept, and engage. But if detection is delayed, those options shrink rapidly. Stealth shifts this timeline. It reduces the time available for the enemy to react. It creates confusion, forcing operators to question what they are seeing. Is it a real target or just noise? Is it worth responding to? That hesitation can be enough to allow a stealth aircraft to complete its mission. Another important point is that stealth is directional. An aircraft is typically optimized to be least visible from certain angles, particularly from the front, where it is most likely to face enemy radar. From other angles, such as the side or rear, its radar signature may be larger. This means that stealth is not a constant state. It depends on positioning, orientation, and the type of radar being used. Pilots and mission planners must take these factors into account, choosing routes and tactics that maximize the aircraft's advantages. In the end, stealth is not a single technology. It's a system of design choices, all working toward the same goal. It requires compromises, trade-offs, and constant refinement. What makes it seem mysterious is not the concept itself, but the way it is often presented. Once you break it down, the idea becomes much clearer. Radar sends out energy. Stealth aircraft are designed to control how that energy interacts with them, deflecting most of it, absorbing the rest, and minimizing what returns. Understanding how stealth works in theory is one thing. Seeing how it's applied in real aircraft is where the concept becomes clearer. The most important examples are the F-17 Nighthawk, the B-2 Spirit, and the F-22 Raptor. Each of these aircraft was built with stealth as a core principle, but they interpret it in very different ways. Together, they show how stealth evolved from a narrow experimental concept into something more flexible and integrated. The F-117 Nighthawk is where stealth became operational reality. It was not designed to be a traditional fighter. It doesn't rely on speed, agility, or air-to-air combat performance. In fact, by conventional standards, it performs poorly in those areas. That's because its design priorities were completely different. Everything about the F-117 revolves around reducing radar detection. Its faceted shape, made up of flat angled surfaces, is a direct expression of early stealth theory. Instead of worrying about aerodynamic elegance, engineers focused on controlling radar reflections as precisely as possible. The result is an aircraft that looks unusual and even inefficient, but is extremely effective at its intended role. This design allowed the F-117 to do something that was previously very difficult: penetrate heavily defended airspace without being detected early. During operations, it was used to strike high-value targets in areas protected by advanced radar systems and surface-to-air missiles. Its success demonstrated that stealth was not just theoretical, it could work in real combat conditions. However, the F-117 also reveals the cost of early stealth. It carries a limited payload, has subsonic speed, and depends heavily on planning and support. It's not versatile. It's a specialized tool designed for a specific type of mission. This reflects an important truth about stealth at that stage. It required significant compromises. The B-2 Spirit represents the next step. Instead of focusing on a narrow role, it expands stealth into a strategic capability. The B-2 is designed not just to survive in defended airspace, but to travel long distances and deliver substantial payloads while remaining difficult to detect. Its flying wing design is central to this. By eliminating vertical surfaces and smoothing the entire structure, the B-2 minimizes radar reflections across a wide range of angles. This makes it one of the most difficult aircraft to detect, especially at long range. What makes the B-2 different from the F-117 is scale. It's much larger, carries more weapons, and operates over intercontinental distances. This means stealth is no longer just about getting in and out. It's about maintaining low observability over extended missions. At the same time, this level of capability introduces new challenges. The B-2 is extremely complex and expensive. Its stealth coatings require careful maintenance, and its systems demand a high level of support. This limits how often and how widely it can be used. It's not a routine aircraft. It's reserved for missions where its unique capabilities are essential. Then there's the F-22 Raptor, which represents a shift in philosophy. Instead of building an aircraft entirely around stealth at the expense of other qualities, the F-22 integrates stealth into a broader set of capabilities. The F-22 is not just difficult to detect, it's also fast, maneuverable, and equipped with advanced sensors and weapons systems. It can operate at supersonic speeds without afterburners, engage targets at long range, and still perform effectively in close combat. This makes it a true multi-role aircraft. Its stealth design is more refined than earlier examples. It uses a combination of shaping and materials to reduce its radar signature, but it does so without sacrificing overall performance. The result is an aircraft that can operate in a wide range of scenarios, not just specialized missions. This evolution from the F-117 to the B-2 to the F-22 shows how stealth matured over time. It started as a focused solution to a specific problem and became part of a larger system of capabilities. But despite these advancements, stealth has never been perfect. It has limits, and understanding those limits is just as important as understanding how it works. One of the most important limitations is that stealth is angle dependent. Aircraft are typically designed to be least visible from certain directions, especially from the front. From other angles, such as the side or rear, the radar signature can be larger. This means stealth is inconsistent. It depends on how the aircraft is oriented relative to the radar system. Pilots and mission planners must take this into account, choosing routes and tactics that minimize exposure from less favorable angles. Another limitation involves radar frequency. Not all radar systems operate in the same way. Stealth aircraft are usually optimized against specific frequencies, particularly those used for targeting and fire control. These radars are the most dangerous because they guide weapons. However, lower frequency radars can sometimes detect stealth aircraft at longer ranges. They are less precise and may not be able to track or target effectively, but they can provide early warning. This creates a layered detection environment where different types of radar complement each other. Infrared detection is another factor. Even with reduced heat signatures, jet engines still produce heat that can be detected by advanced sensors. At closer ranges, this can become a significant vulnerability. Stealth aircraft must still manage their thermal output and avoid situations where they can be easily tracked by heat. Maintenance is also a major limitation. Stealth materials and coatings are sensitive. They can degrade over time due to weather, wear, and operational stress. Maintaining the aircraft's low observability requires constant attention and specialized procedures. This increases cost and reduces availability compared to conventional aircraft. Cost itself is one of the most defining constraints. Developing, producing, and maintaining stealth aircraft requires significant resources. This limits the number of aircraft that can be built and affects how they are used. They're often reserved for high-priority missions rather than everyday operations. This is also a strategic limitation. As stealth technology becomes more common, countermeasures continue to evolve. Radar systems improve, detection methods diversify, and new technologies are developed to reduce the advantage of stealth. This creates an ongoing cycle of adaptation between detection and evasion. Despite all of this, stealth remains one of the most influential developments in modern air warfare. Its value is not in making aircraft invisible, but in reshaping how engagements unfold. When you look at the F-117 Nighthawk, the B-2 Spirit, and the F-22 Raptor together, the pattern becomes clear. Each one reflects a different stage in the same idea: control detection, delay reaction, and gain the advantage of time.